Hey everybody, great to see you again. Mr. Smith here. Today's slide deck, we're going to talk about two modes of energy transfer, and what we're going to primarily do is focus these onto a project that we have upcoming in class where we focus on building science and particularly your house. So this isn't your house, this is an industrial building, but what I want to show you in this infrared image is an example of what's called heat transfer by conduction. So conduction refers to typically heat transfer through a solid material, where we have the solid inside the building transferring heat to the edge of the building where the temperature is colder. So a couple things about this. You might notice that the really bright spots or the yellow spots should appear to be warmer as you think about this than the spots right here that are colder. And that should make sense because if you think that energy leaks through windows from your life experience, you'd be right. What's really neat about this is a perfect example, though, of heat transfer by conduction, because you can see a framing member right here, which is either steel or heavy wood, that's acting amazingly even more like a sieve for heat than the windows are. And you can see that by the brightness of the material right there. So if that is really 21 degrees as they shot that image right there on a cold day, that's a brutal source of heat loss. So that's an example of what's called thermal bridging. So in this slide, I'm giving you all of the technical details that you need to know when you think about conduction. So let's dive in on the formula first, and I'll explain that. Q over T is the amount of heat, Q, per time that flows from a material. So A is the area of the two surfaces that are joined. So if I point down to my diagram, you can see that I have one material that's warm, and we're going to call that T1. Another material is cold. So this could be a framing member where this part is the part that's inside the building, and this is the part that's on the edge, maybe against the brick of the outside of the building. And what's going to happen is heat's going to flow from hot to cold on this. So I've got my two temperatures, T1 and T2. L is the length of the material that divides them. Okay, so couple last things. A is the area, it's the cross-sectional area. So basically the more area you put in contact, the greater the heat flow, the bigger the distance lengthwise between the two temperature differences, the smaller the heat flow. And then finally, because there always is, there's a constant. And this is called the thermal conductivity of the materials that are involved. So not surprisingly, there are a lot of different materials and a lot of different heat flows. So this is really worth looking at. If you thought silver was a great conductor of electricity, you're right. It turns out for the same reasons, it's a great conductor of heat. Same thing with copper, aluminum, and as you work your way down, you should see things like fiberglass. That's a material that's used for insulation. Pretty crummy heat conductor, right? What's interesting about fiberglass is we use it in insulation because it traps air, which is actually one of the worst materials in terms of heat conductivity, and conversely one of the best insulators. So what I'm going to do is take you in right now, having given you the formula, to some awesome simulation software. So what you're looking at right now is a fantastic simulation. This is Energy 2D, which was built by the Concorde Consortium, and I think Charles G., the director, actually was involved with this building of this thing. Awesome software. However, it's Java, and there's an issue with Java, so I'm going to show it to you on a video rather than give it to you to play with in the lab. What we're going to do is make a comparison of heat flow through cellulose fiber, a 2x4 stud, and fiberglass insulation. And what we're going to do is just let it run. We'll talk about it as we go. So what you're seeing happening here is thermal energy bleeding from the house, that's this area in white over here, into the cellulose, and then into the fiberglass. So if you were thinking that maybe fiberglass is a little bit better insulator than cellulose, yeah, you'd be right. But what's interesting about this is that wood is actually it's not a great conductor of heat, but it's a lot better conductor of heat than the cellulose. So you should be seeing a warm spot developing right here. That's a thermal bridge, and that's one of the things that you're going to look for as you do your own heat analysis. Now, I'm going to stop this, and I'm going to put a couple of features onto it that we'll talk about in a second. First, I'm going to add a thing called an isotherm. So you'll see what that does in a second. And then, to make it even more complicated, I'm going to add some things called heat flux lines. And then we're going to talk about those right now. Okay, so there are three things that I hope you notice from this. When I added these lines are called lines of heat flow or heat flux. And what they are is just a vector pointing in the direction of heat flow. The thing is that this fits perfectly with an analogy we made earlier in the year. You could think of this as being a high temperature region or just a region where it's a hill and there's a ball that's going to run downhill. These lines that we're going to call isotherms are lines of constant temperature, but they work exactly the same way as lines of constant height on a hill. So when we talked about electricity and equipotentials and lines of charge flow, these are all perfectly analogous. So the math works out the same when you get to a high level. The concept is the same, and it's really cool to see it happen. Anyway, the thing I want you to notice is that when you add those lines of heat flow, you should really pick up on the fact that the heat comes streaming through the stud. So that's an example of a material being a heat bridge. Last thing about this, because of Java security issues, we don't use this app in school anymore, but if you want to and use this on your own computer at home, be my guest. I'm giving you the address for it, and if you want to disable the security permissions and stuff, that's totally fine and on you. But anyway, this is awesome software, and I'm going to show you in a minute an HTML5 version of some of the apps that they did that are pretty good. This is an example of heat bridging in a way that you could study at home. What we're doing here in this image is looking on a very cold day at the outside of a house. What we're going to ask you to do is do exactly that, and also to try the flip side, to go into your basement and look at the sill. So the sill is the wooden plate that your entire house rests on, and if you can get to it, if you have an unfinished basement and look at it from above, you might see some thermal bridging. So on this slide, we're going to summarize a few things that are really practical. Large K materials, those are your conductors. If you have a small K, you're an insulator. What you call the R value of insulation is something that you look at when you look at insulation in the store. And that's just equal to the thickness of the insulation divided by the K. So super practical. This little table, nothing to worry about, but I just wanted to point it out to you. Let's go on and take a look at a real life example where we study this house. So here we've got some realistic numbers for the house. This is a 10-inch thick basement. Comfortable temperature inside, really cold temperature outside. And this number right here was a 40-foot perimeter with 1 foot high. So this is 40 square feet converted to square meters. Anyway, realistic numbers. When we go ahead and plug all those in, all we had to be mindful of doing was to pick out the thermal conductivity of concrete. So not a big number, but look what happens when you multiply all that. You get 313 watts of power bleeding continuously to the outside world, which is going to mean it's pretty hard to keep this space warm. So before we leave the idea of conduction, we're just going to touch briefly on some of the science at the small scale to talk about how conduction really happens. 2 modes. Now let's check them out. So on this slide, I wanted to let you into one of the all-time most powerful, coolest facts about metals. So basically, metals are great conductors of heat, electricity. They're shiny, they're flexible, all that stuff. That's all down to the one thing I'm going to talk about right here. So what makes metals really special is the fact that the electrons that are pictured as these little violet dots are not owned by any one particular atom. These are what are called conduction band electrons. So they're basically electrons that belong to this whole group of atoms here. So they're sometimes called the sea of electrons or free electrons. And what happens is when you talk about conducting electricity, if you put a voltage right here, so you put a minus charge there and a plus charge here, these electrons are the ones that migrate towards the plus. When you conduct heat, the reason that metals are such great conductors of heat is these electrons are the first ones to pick up kinetic energy from conduction and to physically move that by colliding with everything else down the material very efficiently. So free electrons. So next thing is a little bit deeper, but also really cool. So one question you might ask is, if all metals have free electrons, how come all metals don't have the same ability to conduct energy, right? How come they have different conduction coefficients? Well, here's why. Metals, like all solids, live in some kind of crystal structure. And the crystal structure and the nature of the bonds between the atoms is actually complicated. So what we've done here is given you an image of atoms, these gray things, as connected by springs. And that's not too far off from the truth. So if you add energy to a material that's a solid, what happens is the material can vibrate. But the way that those vibrations are made possible really depends on the metal, and it depends on how the bonds are structured. And it gets even more complicated when you start to talk about materials that are really organically complex, like wood or something like that. But bottom line, what you want to think about is where we talked about different ways that water can store energy because of all the different ways it can vibrate. That's true also for materials that are solids. So what I'm showing you here are called lattice vibrations, and those are another way that materials can store and transmit energy. Long story short, if you heat up one end of this, eventually that energy will transmit across the material. And so if I heat up one part, that heat energy will travel downward. It's not as quick or efficient as electron energy transfer, but it's very real, and we'll talk about that one more in class. So the second type of energy flow we're going to talk about is energy flow by conduction, and that's a biggie for all of us because we live in houses. All energy systems, heating systems in your house work basically the same way. They heat up air, and the air is really what moves the energy. The only difference would be if you have radiant floor heat and you literally stand on the hot floor or the warm floor, and that's a whole different ball of wax. That's conduction. The big thing to look out for with convection is you have mass movement of air molecules. So we'll take you a demo for that right now. Before we do, I wanted to show you this formula really quickly. This formula is not one that you need to write down, but just to show you that the rate of heat flow between a radiator and a room, for example, does depend on the same way that conduction did on the difference between the environment and the hot radiator, for example. So works very similarly, but don't sweat the formula. That's not one we're going to worry about. Let's go look at an example of this in real life. So the demo you're going to look at right now is from the HTML5 materials that Conquer Consortium put out. They're not as grindy and technical as the other ones, but they really do the job. What I'm going to show you here is I have on one side heat transfer by conduction through a solid. So that should look very similar and familiar to things we looked at before. But if you look at the example on the left, you can really see the difference between conduction and convection. So why is forced hot air heat so efficient? Well, it gets warm air moving right away. What you're actually looking at here is what would be considered radiant heat from a floor. So the Keefe Center has, for example, radiant tile floors, and what they do is they heat the air directly above the room, and then that warm air goes and fills the space. And what you see is this swirling that's typical of dense and less dense molecules mixing inside of a space. Okay, so more on that later, but a little bit about convection. So we're going to wrap up right now with a real life picture taken with our actual FLIR 1 cameras in the cafeteria at St. John's. So what you can see is a couple of kinds of energy transfer going on. If you saw this purple region and thought the door is cold on the edge, you're right. Those doors, actually most metal doors, have insulation, so some kind of polystyrene plastic in the middle that does a decent job of blocking heat flow. The edges are just metal, and the metals conduct heat. What's interesting about this image, though, is I wanted to give you an example where you can see convection really happening right here. Cold air is infiltrating the building, and so you can see it's literally stealing energy progressively from the floor right here. So if you put your hand down in this area, it'd feel cold, and it looks exactly like what it is. So we're going to study this in the lab. We're going to study this in your house, and it's going to be a lot of fun. So anyway, bring some questions with you to class. We'll talk soon, and take care. Bye-bye.